And welcome back. As we continue our cosmic journey, we've already have started exploring our solar system, but let's go ahead and take a comparison with other planetary systems. So if we want to start studying other systems, what are the things that we need to start thinking about? Well, until the mid-1990s, the practical study of the origin of planets focused on a single known example, our own solar system. And although there had been a great deal of speculation about planets circling other stars, none up to this point had really been detected. Logically enough, in the absence of data, most scientists assumed that our own system was likely to kind of be the typical example. What would they actually see, though, when they started turning their gaze elsewhere? So, once we had the technology to do so, we could start doing some discovery of other planetary systems. Stars, like our own sun, as we know, are formed from dense regions in a molecular cloud made of gas and dust, and they feel an extra gravitational force and begin to collapse. Now, this is a runaway process. As the cloud collapses and we start collecting more and more matter into one point, the gravitational force gets stronger, concentrating more and more material into a protostar. Now, roughly half of the time, the protostar will fragment or be gravitationally bound to other protostars, forming a binary or multiple star system, stars that are gravitationally bound and orbit each other. The rest of the time, the protostar collapses in isolation, as was the case for our sun. Now, in all cases, the conservation of angular momentum results in a spin-up of the collapsing protostar with surrounding material then flattened into a disk. So, if we look at a protoplanetary disk in the Orion Nebula, we can kind of actually get a viewpoint of what this might look like in space. So the Hubble Space Telescope imaged this disk here in the Orion Nebula as a region of active star formation using two different filters. So the disk, about 17 times the size of our own solar system, is in this case an edge-on orientation to us. In other words, we're looking at it from the side. And the newly formed star is shining at the center of the flattened dust cloud. Now the dark areas here indicate absorption, not an absence of material. So this is, in other words, this material is absorbing some of the light energy that's being emitted here. On the left image, we can see the light of the nebula in the dark cloud, and the right image, a special filter is actually used to block the light of the background nebula, so you're not seeing all the light coming out from there, and so we can actually see here in the center the actual star a lot easier. Now, when we start looking at protoplanetary disks, many of the circumstellar disks we have discovered show some kind of internal structure. The disks appear to be donut-shaped, with gaps pretty close to the star. Such gaps indicate that the gas and dust in the disks have actually already collapsed to start forming large planets. The image at left shows a protoplanetary disk taken using radio light. Newly formed planets that orbit the central star clear out dust lanes path as shown in the computer simulation as right. Now, please note that this planet that's here obviously is not to scale, but it does kind of give you some visual representation that this planet, as it orbits through here, is clearing out that path there. So, we can, of course, have a planet in our little disk here, so this allows us to start discovering what we call exoplanets. And you might think that with the advanced telescopes and detectors astronomers have today, we could directly image planets around nearby stars, which again, we refer to those planets as exoplanets. Now, this has proved to be extremely difficult. However, not only because the exoplanets themselves are relatively faint, but also because they're generally lost in the brilliant glare of the star they orbit. The star is always going to be brighter than the planet. Now, the detection techniques that work best are indirect. So they either observe the effects of the planet on the star it orbits, rather than necessarily seeing the star itself. So, the first technique for discovering exoplanets that yielded many different planet detections is a very high-resolution stellar spectroscopy. The Doppler effect, if you recall, which allows us to see redshift and blueshift, lets astronomers measure the star's rate of velocity, that is, the speed of the star toward us or away from us relative to the observer. If there is a massive planet in orbit around the star, the gravity of the planet causes the star to wobble, changing its radial velocity by a small but detectable amount. The second indirect technique is based on the slight dimming of a star when one of its planets transits over the face of the star as seen from Earth. Now, astronomers, in this case, don't see the planet, but only detect its presence from careful measurements of a change of brightness of that star over long periods of time. If the slight dips in brightness repeat at kind of regular intervals, we can then determine the orbital period of a planet, and from the amount of star that obscured, we can actually measure the planet's size. Now the graph right shows the planets that we have found so far using the transit method. The colored parts of each bar indicates the planets detected using two different methods. So we have those that were previously verified and those that have been newly verified with the Kepler approach. Now you'll note that the largest number of planets found so far are in two categories that we don't have in our own solar system. Planets whose size is actually between that of Earth and that of Neptune. Now further analysis of the data to correct for such biases or selection effects that indicates that small planets, like our own terrestrial planets, are more common than giant planets. So if we start configuration for other planetary systems, what are we going to start to discover? Well, this graph right uses gray dots to indicate the planets discovered by measuring the radial velocity. Because remember, the other one is using transit. This is radial velocity, and so the red dots are for planets that transit their stars. In the early years, the only planets that could be detected were similar in mass to Jupiter. Now, improvements in technology and observing strategies enabled the detection of lower mass planets as time went on, and now even smaller worlds are being found. Again, so if you look here, we have our transits, which again are going to be the red dots, and the gray dots are showing us ones with radial velocity techniques. So we are getting much more information in here. This tells us that there are other exosystems, so other places, kind of like our own solar system, that are very similar to our own. If we look here, we can start seeing that this data shows us that these systems are multi-planet. However, the thing that we still need to pinpoint down is whether further measurements are needed to see if these planets orbit in the same plane as our stars, such as our own.